In this tutorial, I'll be covering how to find the pH during a weak base titrated with a strong acid-base titration. So in this kind of reaction, you're titrating a weak base, which I'm showing here as general as just something B. For example, this could be ammonia. Reacts with a strong acid, HA. For example, this could be HCl. The products then are Hb plus because the acid donates its proton to the base, turning the base into Hb plus. So in the case of ammonia, that would turn into NH4 plus, which is the conjugate acid of ammonia. And then you're left with A minus. A minus is the anion of your strong acid. For HCl, that would be the chloride ion, and the conjugate base of a strong acid cannot affect the pH. So, to determine what your pH is, first you must determine where in the titration you are at. So, in an acid-base titration, starting with a base, if I were to look at the curve would look something like this. The pH at the start would be high because it is a weak base solution, and as you add increasing volumes of your strong acid, your pH will start to slowly go down until it suddenly drops right here, somewhere around the equivalence point being wherever you would end up having equal moles of your acid and your base. And then after the equivalence point, you have a very low pH because at that point you're left with excess HCl. So on this graph, the equivalence point might be somewhere around here in the slightly acidic range. So if my pH of 7 is right there, this would be something slightly lower than a pH of 7. So to determine where you are, you're first going to take whatever information you're given and convert them to moles. So if you have more moles of your weak base, then that means you haven't yet reached the point where you have equal moles of acid and base, and you are before the equivalence point. At this point, the strong acid is your limiting reactant, and once you've consumed all of that limiting reactant, you will have a solution of your excess amount of weak base, and you will be producing its conjugate acid. So a solution of weak base and its conjugate acid is by definition a buffer solution. So we use Henderson-Hasselbalch equation to find the pH. So the Henderson-Hasselbalch equation for the pH of a buffer based off of a weak base is that the pOH is equal to the pKb plus the log of the conjugate acid over the weak base. And these can either be in molarities or in moles, as long as they're both in the same unit. If you've determined that you have equal moles of both reactants, then you are here at the equivalence point. Now your both reactants will go to no more moles, and all that you have produced, you have none of these anymore, is your weak acid's conjugate, your weak base's conjugate acid, and then the counterion. So we already said that the counterion of a strong acid cannot affect the pH, so what we're really worried about is NH4. Technically, though, we have an ionic compound here, so that's technically a salt. So if you remember back to chapter 16, at this point it's just finding the pH of this salt. So to calculate the pH of the solution, we're going to need a reaction table, an ice table, where that conjugate acid reacts with water to make hydronium. So make your ice table, find concentrations. Remember, ice tables need to be in molarities, so if you're still in moles at this point, turn that into a concentration, turn that into moles, plug it in. To find the X of your ice table, you'll need the Ka of that conjugate acid, which you can obtain from the Kb of the original weak base using Kw is equal to Ka times Kb. Plug that into your ice table, solve for X. That will be the concentration of hydronium H3O plus at equilibrium, which you can then plug into your pH equation. If you find that you had more moles of your strong acid, at this point you are past the equivalence point. If you're past the equivalence point, now your weak base was the limiting reactant. Sorry, that's a typo. That was a weak base, not weak acid. So you would have excess strong acid. Your weak base is completely consumed, and you would still in this case have weak acid. So we've used up all of our weak base. We still have strong acid. We also have the conjugate acid, but conjugate acids are not going to affect the pH nearly as much as the strong acid. So we're really only going to worry about our strong acid. Strong acids completely dissociate or ionize to make hydronium. So all you need to do is determine your moles of excess acid, convert them to a concentration and molarity, plug that molarity into your pH equation, and that is the pH down here, those very low pHs after the equivalence point. So let's go ahead and look at an example. So here's the example. An analytical chemist is titrating 171.8 milliliters of a 0.6200 molar solution of diethylamine, which is a weak base, with 0.2300 molar solution of HNO3, that's nitric acid, which is a strong acid, and we're given the pKb of the diethylamine. The question is, calculate the pH of the base solution after the chemist has added 130.6 milliliters of the nitric acid solution. So to determine where we are in the titration, we need to know moles of each of our reactants. For both of them, we're given a volume and a concentration. So the molarity is moles per liter, so molarity times liters will give us moles. So converting each of these milliliters to liters by dividing by 1,000, and then multiplying by the number of by the molarity will give us the number of moles. So I've already done that here. So 0.1718 times 0.62 is where the 0.1065 came from, and then for the nitric acid, 0.1306 liters times 0.23 molar is where the 0.0300 came from. So now that we have moles of each, we can easily see that the nitric acid is going to be our limiting reactant, Lr here. We have less of it. So that means we are before the equivalence point, and we need to change our amount of moles by the amount of the limiting reactant. So our reactants are going to be minus and our products are going to be plus. So we'll go ahead and add that amount to the product side and subtract it from the reactant side. So once we've subtracted, we're left with just moles of our original weak base here. No more of the strong acid. And then we are left with moles of the conjugate acid of our weak base. So we have made a buffer solution. So we are going to use the Henderson-Hasselbalch equation to calculate its pH. So after we plug everything into the Henderson-Hasselbalch equation using the pKa that they provided, we found that it had a pOH of 2.48. The pH then is 14 minus that, which leaves us with a final pH of 11.52. So to recap, we identified that we were before the equivalence point. So if I compare that to what I would expect for a weak base strong acid titration, I am somewhere in this area, so I expect a very high pH, much greater than 7, and sure enough, I do get a high pH. So that is how to find the pH of a weak base strong acid titration.